fabricate an all-solid cell. But on top of that, once you start introducing new interfaces, tracking that interface and really trying to understand what's happening in situ is challenging, but not impossible, right? It's just more challenging because now you're trying to basically probe what's happening to the structure at the few angstrom level, and also what's happening to the mechanical properties of these materials as they behave right at the interface, right? So there are definitely ways of doing that, and we can tease out some information from EIS to really try to correlate the electrochemistry to the microstructure, to the evolving crystal structure as well. So that, but doing that as a whole from start to finish is, really a heroic experiment, and it, takes a lot of care. So I thought I'd highlight one example so we can really go into deep dive and compare like the different characterization methods to the electrochemistry. But of course, this is not, the only system that's out there, okay? And this is a relevant material system for some of you in the audience, so it might benefit your proposal. I try to make it somewhat relevant. So the example we're going to look at, and that we've been talking about, and where we left off last time for mixing and matching material systems and making composites, is let's say you take some state-of-the-art nickel-rich NMC. So I don't have the composition here because the sample is the paper does not actually report a composition because this is out of Samsung. So for obvious reasons, they don't report the stoichiometry, the particular chemistry. But that is a minor detail when it comes to this analysis. So what you see here is the NMC sample, and the coding layers outlined in the elemental analysis. So this is coded with lithium niobate. So you see the elemental analysis showing that the niobium atoms are indeed, sequestered to the edge of the cathode particle. So it's nicely distributed and maintained there. The solid electrolyte is an aguridite type of electrolyte. So it's so the anticipation is that if you just mix the aguridite with an oxide, there's going to be rapid decay in terms of the electrochemical performance, and thus you need a coating layer. And so the typical experiments for all of these types of studies would be to make your composite and then to compare it with the bare electrode material or composite. And typically you need to do this under pressure, either to maintain the contact, but it also allows you to mimic how this material would behave in a real life battery, because typically battery packs are pressurized before they go into the electric vehicle. Now, this is just a symmetric cell, so you're isolating all of the components. You haven't made a full cell just yet. So all you're trying to do is track the electronic and the ionic conductivity of this material, and understanding the resistance from ionic contributions as well as electronic contributions will allow you to understand what kind of chemistries are happening at their interface. Because if the hypothesis is that there are chemical decomposition products that are not conducive for ionic conductivity, ionic permeability, ionic migration across this interface, then you would see increased resistances. So this allows you to isolate, this type of symmetric setup allows you to isolate all of the other variables, right? You're just focused on the active material that you're trying to study. And so you can just put put the material in between two ionically blocking current collectors. So this is just stainless steel. That's the Japanese, the SUS is the Japanese notation for stainless steel. Right, so you see here that it's a mixture of both the solid electrolyte as well as the cathode material mixed in. So the cathode material could be bare, and that's the control, or it could be coated with lithium niobate. Okay, so that's what you see. Now the mixture between the amount of solid electrolyte to that of lithium niobate that's coating NMC particles is 72% weight ratio, and that corresponds to a 1-to-1 volume ratio. That's where that number is derived from. And the pressure is just kept at 295 MPa for 2 minutes, so that's pretty high. And resulting thickness is about 320 microns, so pretty standard conditions. So what you want to do is basically try to establish you want to establish contact within all the composite components before you run this experiment. Now, what typically will happen, of course, is there will be volume changes that will occur, and that will result in increased impedances and resistances that you'll eventually measure. But this is the starting pellet. So first off, from just doing EIS, if you look at the Nyquist plots, what do you see? Between the bare that's on the left and the coated particles that's on the right. So you set up your cell, you age for 40 hours, 40 plus hours. What are some of the observations that jump out at you?
Well, impedance looks a lot higher for the coated cell.
The impedance is higher for a coated cell at the beginning, right? Initial contact. So no resting just yet. For the coated, seems to stay the same, which means the inverse is true, which the bare is growing. Okay. So now, is that expected or unexpected? Why would you expect that, Matt?
The bare is not stable. As stable with the different chemical compounds in it.
You would expect the bare NMC particles to have more chemical stability with the solid electrolyte.
Less chemical stability.
Oh, less chemical stability.
That's why we draw in just resting in contact with all the solid electrolyte.
Ah, okay. So let me separate those two thoughts. So you're saying, okay, I was trying to make a sequential segue, but I think we jumped it, which is fine. So your thought is that the growth is a result of chemical instability between the bare particles and that of the solid electrolyte. Your comment is that the rate is not really changing. I mean, it's changing, but not as pronounced as that of the bare particles. So the electrochemistry, just the impedance so far, not even galvanostatic cycling, no current, I mean, nothing. You're basically just measuring the impedance, the response to the AC signal, right? Is that you can already see just sitting there and waiting that there's going to be it's an indication of chemical instability already, okay? So that's a pretty strong indicator of why one would need coating. But by coating NMC particles with lithium niobate to protect the interface, you actually are introducing higher resistances because now you have a new interface. Okay? So it's not always a linear, like a one-to-one effect of, if you add more things that it'll get better. It actually, the rate of change is what is improving, not that the resistance is expected to be less because you're introducing new interfaces, and that's what you have to compensate for. Okay, now what else do you notice about the EIS?
The larger pumps are swapped, like the left versus the right.
Okay, so you're saying the semicircles are swapped?
Yeah.
Okay.
Like the larger semicircle for the uncoated seems to be
Oh, larger in the real amplitude.
Yeah.
Oh, sorry, the imaginary amplitude.
Well, both.
Okay. What implications does that have? Sorry, can you speak up?
Was that when you coded stuff that touch
Yes, so the charge transfer increases, right, initially, definitely. The total resistance, right, is also increasing. Now, in terms of these pumps, these semicircles, what are the contributions from the material itself that would or could potentially result in these shapes? Okay, so capacitive behavior. All right, what would cause capacitive behavior? Like, what about the material property, or how would you describe the material that would contribute to capacitive? Like, where is the capacitive behavior occurring?
less ionic conductivity?
Okay, so okay, there's a drop in ionic connectivity, and where does that typically occur? If you have a polycrystalline sample, say, which these are just powder particles. Between the particle distance, okay. If you have a really, so what would that be called? Oh, anyone can contribute. I'm not trying to put, this is not like let's put my desk onto the spot here. This is a general discussion.
Boundary.
Yes. Yes. So there are defects, right? There are voids, there are grain boundaries that contribute to the overall signal. And you can tease out all of this, you can backtrack all of this data out from the EIS, right? So so you can break down the contributions from the bulk electronic conductivity, the grain boundary electronic conductivity, the ionic conductivity in the bulk, as well as the ionic conductivity at the grain boundary, as has been mentioned. Right? So you can break down all of this so that you can better understand how to design your particle, how to design your material to begin with, and what is the effect, and you can rule out the effect of adding an interfacial layer, like a buffer layer to the coating. And you can do this systematically for not only lithium niobate, but obviously for other oxide solid electrolytes before you interface with a sulfide solid electrolyte, or an agirodite or what have you. You can break down all of these components. Okay, so that is the entire summary of what you all just said, right? So that's what you notice is that first at about, if you had to fit the semicircle, 100, a little less than 100 ohms in terms of the total resistance, and that rate increases quite a bit. But the rate for lithium niobate coated samples is lower. So that's pretty powerful. And so in terms of how to actually break down the individual components, what you see here is you can make a transmission line type of equivalent circuit that we talked about, when we talked about EIS fitting with elementary circuits components. So you have what you typically expect, right? The ionic conductivity through the bulk, as well as in a series through the grain boundary, but the grain boundary has a resistive component as well as a capacitive component, right? Because it can store charge right there. At the same time, in parallel, there's an electronic pathway because this is a mixed ionic electronic conductor. So you have the same components. You have electronic conduction through the bulk as well as at the grain boundary. So you just make the equivalent circuit model like so. What you don't have is the charge transfer. And so we have left out the Warburg impedance here because we don't actually see that in the EIS. All right. So what can you tease out? Well, the first intercept, so we break it down into two semicircles, right? The first intercept, R1, at the high frequency, that's from parallel resistance of Ri, the ionic conduction, as well as the electronic conduction. And so at low frequency, it's basically just electronic conduction at that point, because you really don't have ionic conduction contribution. So you can break down, when you fit the semicircles, what R1 is, and R2 is essentially the electronic contribution, okay? So that's what we have. So essentially, this is similar to a Randall circuit that you would expect, but there's no Warburg, there's no tail at the end, okay? So then we can actually quantitatively map the rate, because now we have time. We know the resistance is increasing over time for the bulk electronic resistance component, and we for the bare samples as well as for the coated samples. And so what we can do then is track that, and it's as a function of the square root of time. So what you see here is for the bare sample as well as for the coated sample. So the bare is in blue, the coated is in red. We can map out a rate constant, so per square root of time, okay? And so that's what we see is the rate for the chemical degradation rate for bare is higher than that of the coated, which is what we saw in the EIS already. But then if you compare that, the bulk, to what's happening at the grain boundary, if you look at the y-axis, you'll see that it's an order of magnitude more, essentially, okay? What you also notice for this rate is that here, the coated sample, the resistance from the electronic is higher, right? And that is all because lithium niobate is electronically insulating. That's expected. The rate for the bare is actually increasing parabolically. So that's telling you that the chemical degradation is happening very fast. The kinetics is increasing, right, as a function of time. Okay. So then if we look at the ionic conduction, and what we see here is the y-axis is on the same order of magnitude as the electronic contribution. The rates are about, similar in terms of the bare rate being higher than that of the coated rate, right? But it's still relatively low compared to the grain boundary. So if you look at the grain, what's happening at the grain boundary for ionic conduction is exactly what you said qualitatively, but now we can quantitatively map out the rate of the chemical degradation as it affects ionic conduction at the grain boundary. So that's what we can do with the circuit model, okay? So from the initial, just looking at the EIS, before you do any quantitative analysis, you can already have a sense of why you would need to coat bare NMC up against a uridite. Yes, Matt?
So two things. So one,
Yes.
will this be a way to differentiate the decomposition products, how much they contribute to the ionic resistance increase versus electric resistance increase, like electrically insulating decomposition products versus ionically insulating?
Yes.
Okay. And then, does this just keep continuing linearly, or does it eventually stabilize after so many hours just being in contact?
Yeah, so it depends. This will basically be capped, more or less. So this is before cycling. Now, this will definitely change and not continue to increase linearly, because as soon as you start cycling, you're going to have, beyond electrochemical instability, you're going to have electrochemically driven instability. And what's going to happen is this model tells you that there are instabilities and that there are decomposition products. But if you produce, let's say, upon charge, right, the oxidative decomposition products of, what have you, the various oxides that, that we mentioned, Those, if they're passivating, like Li2O said, then those will stay, and they're most likely not going to induce any more reaction, and thus the linearity is not anticipated to continue. But what's going to happen is upon discharge, you're now starting with a slightly different amount of your starting material composition, and that will induce another set of chemical decomposition products, as well as products from the electrochemical decomposition. Some of that's irreversible, some of that is passivating, as in you lose active material, but it stays there and it's stabilized, and other times it's not, it's quite reactive. And that's what you find, is that when you make these interfaces, you can actually induce further degradation because the surface is high energy. So it depends on the material as well,
Would that kind of decide whether or not it is a stable compound or stable setup versus unstable, just continually decompose until it no longer works at all?
Yeah. Yeah, and so with the oxides, when we went through the list of possible decomposition products, the binary oxides tend to be stable, the fluorides as well. But when you start dealing with the sulfide compounds, those are extremely dynamic. And also, once you have the binary sulfides, the mechanical properties actually allow the material to sort of spread out a little bit more and have more contact, and thus now you have a larger surface area of reactivity to produce like H2S and other decomposition products that can be accelerated. So the saying is, it's a dynamic process which changes from cycle to cycle, and it's not, well, it is obvious. Once you understand what the decompositions are, you can predict and screen if these trends are going to continue. And for the oxides, it's mostly passivating. But for the sulfides, it's not necessarily the case. It's quite reactive. Yeah. But the advantage of the sulfide, though, is that because of because of the mechanical properties, because they're not as stiff of compounds, you actually have improved wetting ability with the electrode, and that will actually compensate for the delamination and volume changes that you see in the oxides. So how much of compensation depends on the material until you run the battery. It's not something that you can always predict like ab initio or a priori. Okay. So in terms of trying to understand the volume changes and also the cracks that form, here they show the bare NMC with the solid electrolyte, and here's the coated. And supposedly there's more cracks and delamination in the bare samples that are all on the top. And also this is aged for 5 days. So the yellow arrows point to the cracks and such that you see over time because of the decomposition. They result in these cracks and volume changes. That's a little bit less obvious to me from these images, but that is, the claim. So now tying the EIS to that of the actual, what are the chemical, what are these products that are occurring at the interface that are being produced? What are your observations from this, from the SIMS data? So what you see is basically the count, treat it as count. That's intensity as a function of time. So what you're doing is you're sputtering and you're etching away, you have your cycled sample, or you have your age sample, I should say, and now you're etching away the surface over time. What are your observations from bare on the left and coated on the right? To make it easier for you, look at the age samples. There's a lot of data on this one plot. what are your observations for the count of NiO species? So nickel would obviously come from your cathode itself. It only occur in the cathode.
Lower for the coated cell?
Lower.
Region?
Oh, you mean in absolute quantity? Okay, so I should say SIMS is a very sensitive measurement. So, okay, so you're saying this quantity is a little bit lower than the saturation point after the same amount of time for the aged but uncoated. Okay. Once the NiO count reaches saturation, though, what you'll notice in the blue is that it takes longer for you to etch down to get to the nickel in your cathode for aged bare samples versus aged coated samples. So if it takes you longer to sputter to get down to your cathode sample, what is that telling you about the interface?
If it takes longer to touch down,
Mhm.
then the interface is working.
Yes. You have, for the bare sample, you have a thicker interfacial, interphase thickness that has formed. That goes back to the more decomposition products that are formed without coating. Okay. So that's what that's telling you. So that's in line with the EIS, right? If you have thicker interfacial area, you would expect them to have a higher resistance. And if your material is not, an electronic conductor, then also that means you have higher resistance for the electronic conduction as well as the ionic conduction, right? So it's corroborating what you already see and know from EIS from the beginning, okay?
Is the additional
Oh.
thickness from the coating layer, like, not much of a difference?
Like
Like
what's not?
uncoated versus coating, you have to get through the coating layer too when etching it?
Mhm. Yeah, so the baseline is that there is some interfacial thickness, period. So that's pretty similar, but once you age it, that's the issue. Once you age for, I believe this is 5 days, that's the issue. So this is even, before you start doing any cycling, right? Just aging, there's already chemical instability at the interface.
It's really comparing the same one, fresh and aged, because the coated one would have a thicker interface before aging.
The
Before
coated one would have
cycling.
thicker, yes, slightly. The time difference is pretty slight.
Okay, but you say you more look like a change between the,
The age and the age. This is, the more dramatic indicator of, and so you can also track, because this is secondary ion mass spectroscopy, you can get the signal and the count for exactly what the species are based on the mass, right? So you can have some chloride decomposition, some sulfide, some phosphate, some sulfite, some LiCl2, which is unusual, some sulfate, some lithium chloride, and then you also have the NiO from detection from the beginning of your cathode material as well. Okay. So,
Quick question.
yes.
Just to make sure I got that right. From the edge sample, the blue region,
Yes.
the bare and coated,
Mm-hmm.
it takes you not a long time for you to observe nickel oxide from the bare sample
Mm-hmm.
relative to the coated.
Yes.
So that means that there's a lot more stuff on the interface of the coated one than the uncoated, which is extent because of
Oh.
the coated.
No, sorry. The inverse of what you said is true. Wait, you said the bear?
Because the nickel oxide is from the NMC.
Yes.
So if you start measuring and density, immediately you start aging. That means you're already reaching the cathode.
Yes.
But if the coated, it takes you a while before you start observing it, which makes sense because they say coat creates the coating.
Yes, okay. So it takes you, yes, it takes you slightly longer for the fresh. So you see the difference is minimal, is minor. For age, it takes you less time for the coating because there isn't as much, there is a thinner shell from the decomposition products because of the increased chemical stability due to the lithium niobate protecting the cathode layer. If you don't have it, if you don't have the coating, it takes you longer because the interfacial thickness is larger because of the additional decomposition products. So what I'm hearing is that the inverse of what you said is true, if I understand you correctly. Okay, I think
You're
you.
talking about pretty fresh.
Oh, you're talking about
Original.
fresh.
Yeah.
Yes. Okay, we're in agreement. Okay, thank you for the clarification. I thought I was following. I kept hearing age. Sorry. Okay, so now when we get to galvanostatic cycling, what we see initially is, so the 5-day rest is, is yes. So with and without rest means you've aged it for 5 days. Okay, so if you just run it fresh, what you see is the bear actually has a smaller hysteresis than that slightly of the coated sample. So that's what you see here. So that's in the blue without rest. So you compare the two blue galvanostatic cycling plots. Now, if you do age it and rest, that's what we've seen, is that the hysteresis, the voltage hysteresis is actually smaller than that for the coated than that of the bear. Okay? And while you can get the initial charge capacity to be a little bit more, even with aging for bear 247 milliamp hour per gram versus coated, right? You have now less active material, or rather the initial is 222 milliamp hour per gram. The capacity retention, though, if you look at it, is more significant for coated over time. Okay? So let that sink in. So while you can achieve slightly more initially, the retention is abysmal when it compared to the coated sample, okay? Because of the chemical protection over time. And it goes back to the passivating argument that the interfaces that you form help to stabilize the interface. And if we track the capacity as a function of cycles, so over time, and also the energy efficiency. So you probably have heard of Coulombic efficiency. Well, we've discussed Coulombic efficiency. If you multiply that by the voltage efficiency or the voltage hysteresis, you get a number that is the energy efficiency. And you see what you would expect is that the capacity over time is retained much better for the coated sample with or without rest relative to that of just the bare samples over here. So with rest is in orange, without rest is in blue here. But the capacity retention is slightly higher at 65% versus 59% for the for the sample. Energy efficiency is similar. You can retain higher energy efficiency for coated versus uncoated. Okay, so while the coating adds, more money, expenses, as well as manufacturing time, the cell performance over time is maintained. Okay. And this is all at room temperature, by the way, which is important. Okay, so we talked about one example in depth. We